Hello everyone, my name is Daniel and I'm a programmer and an artist, and these are all my geometry node assets which are available for free on Gumroad. The last update to it was all about arrays and deforming meshes in various ways, and I wanted to go through some more of those nodes. So I thought about doing the array two-dimensional, but it's really just it's very similar to the array one-dimensional. You just instance things twice, and one for the x-axis, one for the y-axis, and then so you have to calculate a few more vectors for offsets, but it's really similar. So I thought maybe instead of doing that, we would look at the array fit quads node. So let's take a look at it and its options. So the first option it has is whether or not you calculate the origin. If you check this box, it basically will make a bounding box around everything, and the center of it will be used as if that was the origin of the object. Otherwise, the orange dot, wherever that is the origin. Then you can keep the source mesh that the instances are spawned on, or you can only keep the instance meshes. Then you can adjust the size, so if you want to squish more elements into each face, you can kind of control that there. And then space allows you to kind of add spacing between elements to some degree. So that's all it's got for options. There's probably room for a few more, but that's what it has for now. Let's go ahead and go through the nodes. The first thing we're going to do is get the domain size. So I guess the input geometry on this is a mesh, and we're going to be spawning an object that we choose on each face of that mesh. So we're going to take our spawner geometry, and we're going to figure out how many faces it has, and then we're going to duplicate, and then we're going to create a duplicate of our instance geometry so that we have one copy for each face in our input spawner mesh. And then you can see here that rather than just using that object directly, obviously we use the object info node to get the object as an input in the modifier, and then get the geometry of it. Then we're going to scale the instances. The as instances checkbox should be true for this to work, and then we're going to scale those instances by our adjust size, which is how we can squish more in and stuff. From there, having one copy of that instance for each face, we need to know how big it is so we can figure out how many extra instances we need to make to be able to fill other faces. So to do that, we're going to realize one of our scaled instances and use the calculate size node group that I think we've looked at before. It does a bounding box and subtract the minimum from the maximum to get a size. And then we're going to scale the minimum of our bounding box by -1 and use that as an offset on a set position node for all of our instances we copied. So essentially what that'll do is it will move the origin of the object to the minimum corner, wherever that happens to be. So then obviously that goes into a switch, and that switch is the calculate origin option. So if it's false, we just use the instance as it was, and if it's true, then we do that set position to the negative minimum. So now here we have all of our instances with the origin where we want it, whether it's in the corner or the original. Then we're going to make more copies, and this time the number of duplicates we want to make should be equal to the number of instances we need to best fill the faces of that particular face of the mesh. So to do that, we need to know an amount, and to get the amount, we have to calculate the size of, or we have to compare the size of the mesh we're instancing to the size of the face where you want to instance it on. So that all comes from some math. Obviously, the first part is from that calculate size node we looked at. We can take the size, we can add the spacing value that you can adjust in the modifier to it. And then we can separate that into its X, Y, and Z components and use the dimensions of the bounding box to divide the faces into segments. So then the other half of that is we need to know how big the faces are. And so now here we have our input geometry. That goes into this vertices of face node. For this to work, we need to know the index of the face we want to look up the vertices for, and we can get that by passing the duplicate index of the instance, where we made one duplicate for each face in the domain size of our geometry, is the index into this vertices of face node. And then sort mode 0 uses the default vertex order that the Blender creates for the faces. And 1 tries to sort the vertices of the face so that they move in, I think it's a clockwise direction, depending on which one's the most downward facing. Or anyway, we'll go into that in just a second. Let's take a look at this vertices of face node. So I guess just sort of going backwards through this, we're going to sample an index from the faces of our input geometry, where the index of the face is passed in through this index input, which again is the duplicate ID of the instances we copied for each face. And then all of these sample index nodes get passed a value. The 1 is the normal of the face, because we want to know that. And the rest of these get a value from another sample index node, but this time operating on the point domain of the input geometry. And they just all pass the position through. The tricky part is we need to know the index of the vertex we want to look up. So we can get that index with a verts of corner node, where the corner index we get from the corners of face node, where the face index comes from our index input again, which once again is the duplicate ID of the instances we copied. Then corners of face has this weights value, and that allows you to sort the vertices so that I think it's whichever vertex gets the highest weight value is at sort index 0. So if we pass a weight into all of these where we've sorted the vertices somehow, then we can get sort index 1, 0, sort index 1, sort index 2, 3 to get our 4 corners of our quad. So the first thing to note is this value if we want to calculate the order of the vertices, the value we're calculating goes into the weight socket, and that operates on the face corners domain. So if we use an index node, we're getting the index of a face corner. Now the basic idea behind this set of nodes right here is to look at the edges, the corners of our face. So we have corner 0, corner 1, corner 2, corner 3, say, and we're going to find this edge, and then we're going to turn that edge into a vector, so a direction, and then we're going to compare that direction to down. And then we're going to take this edge, and we're going to compare that vector to down. And then we're going to take this edge and compare it to down, and so on. And we're going to find the one that best matches down, which is this one. And we're going to rearrange our vertices so that the count starts from this vertex, no matter what it was, and goes around in a clockwise direction. Or at least that's how I intended it to work. It might go counterclockwise or something, but that's the basic idea. So to do that, what we want to do is take our face corner index, get the face that corner belongs to. We're going to get the index of that corner in the face, so it's going to be 0, 1, 2, or 3, assuming it's a quad, which is what this is supposed to work on. Then we're going to add 1 to that index, so if it was the third index, or the last index in the quad, it would become 4. Then we're going to do modulo 4, so if it is the last index, it becomes the first index, 0. And then we're going to use that to get the next corner in the face. So our face index passes through. It's the same face we're working on, but the index we want is the next one, the index we started at plus 1. Then if we have our face corner index again and our next corner index, we can get the vertex at those 2 corners. We can then evaluate on the point domain the position of those 2 vertices. And then if we subtract the current vertex from the next vertex, we get a vector of the direction from the current vertex to the next vertex. Then if we normalize that vector, it'll make its length 1, so just a vector that points in a direction. And then if we take the dot product of that vector compared with down, we'll get a float value between -1 and 1, where it would be 1 if the vector of our edge also pointed straight down, and it would be -1 if the vector from the current vertex of our edge to the next pointed straight up, and it would be 0 if it was horizontal. So then we're going to take the result of our dot product calculation, and we're going to plug that into the weights of a corner of face node, where the face index is the same face we've been working on, which we can get by passing our corner index into the face of corner node and getting the face index. So then for each corner of the face we're working on, so say we have a face and the indexes are 0, 1, 2, 3, and this is our face. And we'll say that this is face 4. So then for each corner of this face number 4, we're going to take the corner index and get the face index, so face 4. And then we're going to look at all the edges of face 4, which might be like this. We're going to find the edge that points most downwards, so that's this edge. And we're going to take the starting corner of that edge, which is corner 2 in this case, and we're going to use our dot product sorting weight to find that for no matter what corner we have. And then we're going to take the index in the face that our current corner is. So the corner index is an arbitrary number because it, I think it's increases across the faces. So the first face might be 0, 1, 2, 3, 4, and then the second face might be 5, 6, 7, 8, etc. But the index in face is going to be 0, 1, 2, 3 for every face. So we're going to take the index of that corner in the face and we're going to add it to the corner that is at the top of the vector that points most down. So that's 2 for this arrangement. We're going to get the index in the face of that corner. So it's index number 2 in this case. We're going to subtract that from 4 and then add those together. So let's just see how that works because I don't really know how to explain it other than showing it. In this arrangement, the corner that if you draw a vector to the next corner faces most down is 2. So if we have 4 minus 2, that equals 2. Then if we add that to the index of all these vertices, we'll have 2, 3, 4, and 5, right? Well, then if we do a modulo 4 on that value, we would have, we'd have here, this would become 0, this would become 1, this is unaffected, 2, 3. If we looked at a different arrangement, let's say the 0 is here, 1, 2, 3. By the way, it should always go around clockwise because I think that determines the normal orientation. I should probably test that, but so then we have our edges, right? So we find the one that faces most down, it's 3 in this case. We do 4 minus 3 equals 1. We add 1 to this, it becomes a 4, 1, 2, 3. The 4 modulo 4 becomes 0, 1's unaffected, 2's unaffected, 3's unaffected. We have the same order we had before, right? That works for every arrangement, no matter where the 0 in the count is, that's going to work every time. So now we have a value that should sort of consistently pick this top left corner as the starting point of a count that goes around clockwise. That's the theory. I don't think it works perfectly if the face is completely flat and the normal of the face, so that the normal of the face would point straight up. But it is the most consistent way I found to prevent all of the instances facing random directions like this if you turn it off. So it's a lot of nodes to do a fairly simple thing. Hopefully that makes sense. So anyway, we take that value, we plug it into the weights of our 4 corners of face nodes. We select corners 0, 1, 2, 3, and 4. We get the vertices of those corners. Then we sample the position at this index that we calculated, where each vertex is a corner of our input face. And then we sample that value, then we pass that value to another sample index node. This time we're sampling on the index of the face, where the face index is gotten from the duplicate index, where we made one duplicate of our instance for each face. Hopefully, I explained that in a straightforward way. Then we just output all those values as the normal position 0, 1, 2, 3. So now we have a node that takes a face index in and an input geometry and returns for whatever index you selected for a face. a position of the vertices, assuming it's a quad. So then using that information, we can subtract all of those corners from each other to get the vectors of the edges again. And then we can use the length node to measure how long those edges are. So you can see here we calculate the 4 edges, we get the length of the 4 edges. If we add those together and divide them by 2, we get the average length of the vertical edges and the average length of the horizontal edges, or vice versa, I don't remember. And then we take the x and y sizes that, if you remember before we looked into the verts of face node, we get the size of our instance here and add our spacing to it. We take that size, separate it at x, y, z, and then we divide the size of our face by the size of our instance and round the result to get a count of how many instances we should create for the x and y dimensions of the quad. If we multiply the result of those two calculations together, we get sort of the squared area of the number of instances we need, and we can plug that into a duplicate elements node where for each instance we created for each of the faces, we create more instances depending on that face's area. Once we've duplicated the instances, we have the correct number to fill the faces. It looks like this, by the way. They're all in the same place, but we have the right number. So then we want to position those instances so they're all in a sort of two-dimensional grid where each grid is a size that best matches the face it's assigned to. So we can do that with this index to coordinates node, which is one that's also used in the two-dimensional array. What it does is it takes in an index, which is the duplicate index of our second copying, so say a face is 2 by 2, it's going to get 4 instances assigned to it. And so then the duplicate index would be 0, 1, 2, 3 for that face. But then the next face is some other size, right? It's going to that duplicate index will restart at 0 for that face. So then we pass that index into this group as well as the size of the face in the x direction. And then it's going to output x and y coordinates to position the instances. So the way it does that is the index modulo the x count is the x value. So it'll go up to 1 minus the size and then reset to 0 every time. So that's how you get your rows. And then the index divided by the x count will be 0 for the whole first row. Or the index divided by the x count floored will be 0 for the whole row. And then once it goes beyond that first row and the modulo resets to 0, the index divided by the count will increase to 1. So then we can output that to the y coordinate. So that's sort of your rows and your columns, so to speak. And then if you take that column or that row value, the y value, and you modulo it by 2, you get every other row, which I don't use here, but it's key part of the two-dimensional array node. So now we have coordinates. Those will be like x0, 1, 2, y0, 1, 2. We need to scale them so that their value is the size of the instance. So say the instance is half, instead of being 0, 1, 2, we want 0, half, 1, 1.5. So we just take our size again with our added spacing, split x, y, z, take each component, scale the individual components by our count. So this is applying on each instance, obviously. Add them together, and then that vector we can use to set the positions of all of to make our grid, our two-dimensional arrays that we're going to place on the faces. Once we have that, the mesh is ready for deforming, so to speak. So we realize the instances and turn it into a mesh. Once we've converted our two-dimensional grid arrays into a mesh with realized instances, we want to set the position of those grids we created so that they match the original quads they are assigned to. So we do that with another set position node, but we have to calculate this vector that we're going to use to assign the positions. The way we calculate that vector is all the way back here, where from our verts of faces node, we output the normal, so that's going to match the z-axis of our arrays, and then the positions of all our vertices. We send all of those over here. So So then we have these 4 nodes here, and they calculate the XY, or they convert the XY and Z axes of the input arrayed instances into the sort of coordinate space of the normal of the face. So the first one here is takes the normal as the input, and we scale it by the Z-axis of the instance. So say we have a mesh, and let's say it's, and this is our Z-axis, X-axis, and our Y-axis. So then, however tall the mesh is in the Z-axis, that vertex will get pushed that far along the normal direction of the face. Then we have these 2 mix nodes. They will take our input face that we're copying, whatever it is, and it'll make an edge in this direction between these 2 vertices, and a second edge in this direction between these 2 vertices. And then depending on how far, so the input value on this, mix node is a factor between 0 and 1, which I'll show you how we calculate that in a second. And if it's 0, those 2 mix nodes will output here and here, these 2 corners. And then as it increases up to 0.5, it would output here and here, these 2 points halfway between along the edges. And if you went all the way to 1, it would be here and here. And then the 4th node mixes the results of those 2 together. So say we had 0.5 for our x-axis, and then for our y-axis we had 0.75. It's going to do the same thing, but this time mixing between the 2 points we calculated. So it would go 75% from this position towards the second one. And that's how we calculate the point in 3D space that we want to remap our axis-aligned XYZ instances to the mesh quad that can be in any orientation and deformation. Hopefully that makes sense. To calculate those factors, all we have to do is to use the separate XYZ node, we need to know the vector we should plug into it. And I just realized I had this overcomplicated, so I've simplified it. So the value we want to plug into that is for the z-axis, we can just use the value as is. And then in the x and y-axis, we want a factor between 0 and 1 for how big that instance is, essentially. And the way we can do that is by dividing the position of the vertex by the size of the grid we created. We can calculate the size of the grid we created by doing a combine XYZ node, where we simply take the instance size that we have and then the count we calculated for how many we needed on the x-axis and how many we needed on the y-axis. We can multiply the x size by the x count and multiply the y size by the y count to get the total x size and y size of the whole grid. Once we have the size of the whole grid, we combine it, divide the position of the vertex by the total size of the grid, and that gives us a value between 0 and 1 on the x and y axis, and then because we left the z axis at 1, it's the position divided by 1, which remains unchanged. So then using that, we pass those into the mix nodes and the scale nodes. We use that to recalculate the XYZ axis aligned position of the vertices to the face aligned and deformed position of the vertices. Then we add the normal offset calculated from the z-axis to the mixed face positions. If you just put this mix node in like this, it would make the mesh perfectly flat, but then adding that normal offset pushes them away. And we plug that value into the set position node. Then there's just the final option. If you want to keep the source, you can join the original geometry to our instances we created. That goes into a switch with the boolean, and then we output the result. So that adds the plane back in. So that's what this node does. It could have more options, I'm sure, like an option to not stretch at all, or other things, but we'll get into that later on. All my nodes are available on my Gumroad page. They're free, and if you want to give me something for them, I always really appreciate that. I'm planning to go through some of the other nodes that I just added to this set these ones here in more detail next. But yes, that's all I've got for now. Hopefully you found it interesting, and thanks for watching.